Hi, I'm Scott Borthman, and today I want to share with you some tips about importing data into vZome. So let's get started. So if you've noticed, vZome has several formats that it can export, but it really only has these three formats that it can import. And many people have asked about this. And why is this? And in fact, you'll notice that three of the formats that it exports are those that it imports. So what's going on here? Well, let's make just a little B0 strut here and take a look at the properties to illustrate something. Notice that the start vector is 0, 0, 0. The end vector is stated in terms of this expression. Each of the coordinates is an expression in terms of phi. So this is -1, -2 phi, and phi, etc. The offset is likewise stated that way. The length in orbit units is stated that way. vZome is representing all values internally with exact values, with exact integers, for many reasons. And one of them is that we never have to try to approximate anything and determine if two balls are in fact the same point. They either are or they aren't, because it's exact arithmetic. So internally, these pairs of numbers are what vZome uses to represent these points. So this is just a presentation of that vector. And you can imagine that that's a challenge for vZome for importing data, because data out in the wild is usually stated in terms of floating point numbers. And there's no identification of how many, what's the multiple of phi in there or anything like that, the golden ratio. So, so that's the reason. Before we go on, I want to show you actually that if you copy this, I'm going to do Command C and copy that. What's on the clipboard is actually going to be this color mesh JSON format. So if I go to my text editor and paste, you'll see this is the text that's in the clipboard. And let's get my little image out of the way here. You can see that this is the array of vertices. So it'll be two vertices. Each vertex is represented by 3 coordinates. So that's a vector. And this is 1 coordinate value. So that's 0. We've got 0, 0, plus a 1 for a divisor, another 0, and another. So that's the origin, 0, 0, 0. The 1 is because we do want to support intersections and generally doing division. So that means I was lying a little bit when I said 2 integers. It's actually 3 integers representing 2 rational numbers that vZome is storing initially, internally. So here's the value of 1 plus 2 phi divided by 1, and so on and so forth. So that's what vZome needs, and that's why we can't find that out in the wild. Okay, we've also got the additional balls and colors, etc. We don't really care about that for this purposes of this video. All right, so let's look a little bit more at the simple mesh JSON format. So I'm going to show you, first I'm going to show you the experience of importing one of these. So let's do this. Import simple mesh JSON. You have an option to set a scale and a rotation. Now this will be a 4D rotation in case this import data has 4-dimensional polytope data. In the case of the file I'm going to show you, it actually is 4-dimensional data, and we have to project it down to 3D. And before we project it, we have the option to rotate the object with respect to our projection plane. That's what this quaternion is for. The scale is actually, you'll see the reason for the scale a little bit later. It's not enabled, so you can put whatever you want in here. It won't matter, so you should ignore it. But the quaternion does matter. But I'm going to leave it as the default quaternion for now and continue, and I get to pick my file. So this is a simple mesh JSON file for the grand antiprism. That's the data that I have available. And okay, you can see it appeared. It's very small. Let's get rid of our extra balls and struts there. And so there, it's very small. So that's the reason we need a scale, because often the easy numbers to manipulate in the file are too small for vZome's use. So we want to scale it up. So I'm just going to go ahead and do that. Scale it up a few times. Doesn't really matter for our purposes now. There's nothing but panels in this file, right? And so I'm going to just start deleting a bunch of panels. And you see I have triangles. There was one pentagon, that's a pentagon. There's a triangle. And you'll see it's got some internal structure. That's because this is a 3D projection of a 4-dimensional polytope. That's usually the interesting case when you're trying to import this data. Simple 3D polytopes, they're easy enough to build in vZome itself. But when you're trying to deal with 4D polytopes, you really need the data set. So that's what we're after, is a file that lets us import and deal with an object like this. Ideally, it would also have balls and struts in it. This one doesn't happen to. Okay, so what does that file look like? So here's our simple mesh file for that grand antiprism. Like the colored mesh JSON I just showed you, we have a list of vertices, and there's a lot of them, right? And you can tell that each of these vertices has 4 dimensions, X, Y, Z, W. Okay, so this is 4-dimensional data, which means vZome will project it to 3D by just dropping the 4th one when it imports it. Again, if you've got a quaternion, it'll perform the quaternion multiplication and rotate the object before dropping the 4th coordinate. We have vertices, we have edges. This is why this thing shows no struts. There are no edges listed. There's also no balls section in this file, which is why we don't see any vertices as balls. Then we have faces. So the faces list the vertex values. So it's pointing into this array of vertices for these for the vertices of the faces. And finally, we have cells, which is good information. vZome doesn't have a way to deal with it at the moment, but you can imagine being able to select an entire cell, say a dodec or a tetrahedron or something like that. We don't have that tool available to us. In any case, this is the format that we're after. Now, suppose you're browsing online and you found some data, some vertex data for a polytope, a 4D polytope. One of the sites you might go to is Eusebia, a very nice site, and it does contain vertex data. So I'm on the home page right now, and the polytope of the month here is the, I'm not going to try to pronounce that, a big complicated polytope. And oops, no, I'm not on the home page. Now I'm on the home page. There we go, polytope of the month. There's a link to the full algebraic coordinates, which is going to take you to the page I was just at, but to the bottom of the page. So here we have a description of the coordinates for that polytope in algebraic terms. Permutations of coordinates, so that means that this is X, Y, Z, W, then all permutations would mean that W, X, Y, Z, and Y, Z, W, X, etc. All those permutations for this one value would have to be applied. And then even sign changes, which means you can have an even number of minus signs that you put into each value. So you have to explode these 3 vectors into all those different options when you try to build this data. But it is possible, just using textual substitution, to get this data into the format expected in a VEF file, or sorry, in a simple mesh JSON file. First thing to note, by the way, is when you're looking at some of this polytope data, this one has the golden ratio, phi, but it also has square root of 2. Square root of 2 is not supported in the golden field in vZome. So at first you might think, okay, this one isn't going to work. vZome doesn't have this field that combines root 2 and the golden ratio. But if you look closer, you'll notice that the root 2s in all cases are in the denominator. So essentially this whole vertex data is being scaled down by root 2. And we can simply ignore that scaling. So what you can do is just ignore the root 2s here, replace those with 1s, and we'll have the data we need to make a go. So this is a golden ratio compatible, vZome compatible data set. So I'm going to copy these coordinate values. And now I'm going to go over to just a simple mesh JSON file placeholder that I had put together. Let's get rid of the edges because that's just garbage. One of the problems with the data that you'll find online is unless you find what's called an OFF file, which won't be algebraic, that'll have floating point numbers. If you don't find OFF, if you just find the algebraic description like we have for Eusebia, you don't know what the edge data and the face data and the cell data is. So you'll be able to get a bunch of vertices to show up in vZome, a bunch of balls, but it'll be up to you to sort of try to figure out how they're connected with faces and cells and edges. So this is the sort of format we're after. Notice that I only have pairs here, so the denominators are actually optional on the import. So I don't need to have a third variable, a third value there on in each case, because it'll be assumed to be 1. So that's what we're after, is that sort of format. And this is what we've got. Okay. So I'm going to give myself a little white space here. And let's tackle these one at a time. So first thing we want to do is get rid of all the divided by root 2's, right? So I can do that safely. I'm going to come back to that one. That takes a little bit of extra work. And just get rid of all of them. We're effectively scaling everything up by root 2. Okay, that's much more straightforward. This we want to, this just becomes 1 over phi. Okay, so those are our 3 patterns that we're after. What you end up having to do is basically figure out what is the expression that corresponds to each of these values and just do a find and replace. Okay, so let's start with this 3 plus phi. Okay, and this, some of the lists of vertices you'll get, the vertex data you'll get will be a lot more. You might have dozens and dozens of rows, and so you have to be a little bit careful that you do the most specific patterns first. So I'm going to follow that. Actually, oops, we don't have many duplicates here. Obviously, we have a few 1s, we have a few phis, we have a few phi squareds, but everything else is kind of unique, and we have a plus or minus 2 plus phi. So let's just do one of these first. So there's 3 plus phi. Well, that's quite easy to 3 plus 1, right? That's 3 plus phi. So that's what we replace it with. And of course, normally I would have to do a find and replace for many copies of that. So here we want 3 plus 2. And here we want 2 plus 1. Okay. And here we have to be a little careful. I'm going to leave the minus sign for a moment and put in 2 plus 1. Basically, we have to distribute the minus sign. So the format doesn't support that. So we're going to distribute the minus sign and get rid of it out here. Okay. What's next? Let's do phi squared. Well, phi squared, the golden ratio squared, is 1 plus phi. So 1, 1 is what we want here. 1, 1. Okay. And there we go. Okay. What about phi? That's easy. That's 0, 1, 0 plus 1 phi. And another one of those. Okay. The 1s we have to put into golden format also. So I have to replace that with 1, 0. Oops. And let's just copy that a couple times. All right, so that leaves us with one problematic issue, which is 1 over phi. So the inverse of phi, well, that's also easy. That is in the golden field, and that is phi minus 1. Okay, so we're going to put -1, 1 for the inverse of phi. So generally, if you have things being divided by phi or powers of phi, you can do a little algebra and you can figure out how to express that in terms of a plus b phi, and that's your answer. Then we do have just the next simple replacement, and this is typically a find and replace. So I'm going to replace all these open parentheses with the open square bracket. And I'm going to replace all the closed parentheses with a closed square bracket and a comma. Okay, so now we have our three prototype rows. Now it's time to remember we have to apply all of those permutations on all of those sign changes. And that'll be a bit tedious, but it's a very simple pattern to follow, right? So all permutations, let's see. I don't remember my combinatorics off the top of my head, but you'll figure it out as you do them. You should check to make sure that you have enough permutations. So that means we're going to be doing things like, let's make a bunch of copies. And first I'm going to replace that and put it over here. So no, I want to put it at the end. It's usually all even permutations. In some cases, it might be all permutations. Here, it's all permutations. So be careful about even permutations. You're only allowed to do an even number of swaps. In this case, we can do all the swaps. So you have to sort of make all the copies, do all the permutations, and then you have to do all the sign change options. Again, it's sometimes all even sign changes. In this case, it's all even sign changes, which means if you add a minus somewhere, you have to add another one, right? You don't get to add you don't just get to invert one of your coordinates or three of your coordinates. It's always all 4 or 2 or 0. Okay, so that's the basic idea. Let's see, I'm going to let's see. We made some duplicates here. Let me get rid of the duplicates. So I have 4 vertices. Let's get rid of the extra comma here and the extra comma here. And just so I can see this a little bit better, I'm going to make some edges. So let's connect 0 to 1 and 1 to 2 and 2 to 3 and 3 to 0. Let's make it 3 to 1, just so we get something a little bit different. So now we have a file that is the right format. It's JSON, it's valid JSON. So I should be able to import this. If I can remember where that file is. Let's take a quick look. On the desktop, okay. So we'll go import our simple mesh JSON. We will not change the quaternion, go to the desktop, there it is. Okay, so there's our simple file. Remember again, we're using very small integers, so typically you'd want to select everything and scale up it a couple times. You can also, when you do things and play around with connecting edges, when you find a vZome orbit as opposed to a white orbit, that's probably a good indication you've got something good. That can vary though. And that's it, really. One more thing. Notice the projection we got there. Let's do this again, but I'm going to show you how the quaternion works. So a typical thing I might do while importing is, instead of using the unit quaternion, which is 1 plus 0, 0, 0, I'm going to make it 1 plus 1i, okay? And that will rotate our object in 4D before we import it, okay? So here we bring it in again. And now we have some nice vZome orbits, okay? So same topology, different geometry, different orientation in the 3D space. Feel free to play around with the orientation, the quaternions, and see what you get. So that's a quick primer on how to import Polytope data into vZome. Thanks for watching. Remember to like and subscribe if you enjoy this. And somewhere here on the channel, you should find the link for our Discord channel. So if you want support or news about vZome releases, etc., please jump on the Discord and join the conversation there. Thank you.